Hello everyone. Hope you guys already listen me. Can you hear me? Hello. Can anyone tell me? Is it hearable or not? Can you hear me?
Yeah, yes, it
Okay.
is.
Okay. Thank you. Okay, so let's start our last lecture. This is the last one. Oh, just a minute. Someone is- Okay. Let me share my screen. Can you see my screen? I think yes. Okay. Yes, I think yes. Okay, yes. Okay, so let's start our last lecture today. So basically, in the previous 2 or 3 classes, I was just talking about some quark and nuclear physics questions. So it's not basically exactly the nuclear physics whole range. I was just totally focusing on the quark part and as well as that quark model basically and the pattern model and all these things. So it was totally last 2 or 3 classes it was, right? Yes. So right now I want to make oh, just a minute. Now I will say something about the in general questions, like as today is the last day. So I thought that like nuclear and particle physics, within the nuclear and particle physics, how many questions should be there from the nuclear and particle physics, if anyone can go for any NET or GATE or any competitive exam. So right now I will do like that. So okay, let's start. Now coming to the first one, basically I will tell something that before going to each and every question and answer session, we have to know some basic things about nuclear and particle physics. And I already told these things in the previous lectures also, but right now I am also telling the same thing because I think that someone was missed the last lectures. So basically what it is I have taken here is it is a table. So this table shows that how many quantum charges are there in the left column, and what type of interaction conserve what type of quantum charge. So this type of things is a simple table like thing you can see, and here the note is there. This note is very important as my consideration. The note is like baryon number, lepton number and electric charge. These three should be conserved in all nuclear reactions. So when you are talking about any nuclear and particle physics reactions, then obviously 90% of the question is coming from the from like that. You are giving a one equation and you have to tell that this equation is allowed or not, and also if it is allowed, then what type of interaction it is it strong, is it electromagnetic or is it weak. So this type of question is 90% as per I know. So that's why I have just taken one table like that, and after that I have just taken a bullet form that baryon, lepton and electric charge should be conserved in all nuclear reactions. And then I was just mentioning one table here. This table basically very important for nuclear physicists and particle physicists throughout their whole research work and throughout their whole work. So what is basically this table is, the table is basically in the left hand side we can see that the particle contents are written, and then IJP, I is basically the isospin and J and total angular momentum and P is the parity. So this type of thing is written here, and then the charge of each and every particle is written, and s is the strangeness number. So I have mentioned some of the particles. It is not that these are the only one, but obviously these particles are most important in any questions of nuclear and particle physics. That's why I have just mentioned this type of this like I think 1 2 3 4 5 6 7 8 9 10 like 10 or 15 particles I have mentioned here. So I think these 15 particles are most important for any competitive exams and all this. So and then after that I have mentioned some leptons as well. So basically whatever it is there, these are the this without this, except this photon, all the things are baryon and meson, like hadrons. And I was mentioning some of the leptons also. And you can also see that the leptons are not strange particles, so that's why for leptons s is dash. Dash means like it is a zero value. So now I have just mentioned some quark constituents. I thought that it is also so very much important, so that's why I was including that as a table form. So you can see that the first 1 2 3 4 5 6 the first 6 particles are basically meson, and the rest of the 4 are baryons. But obviously it is not that these only 4 particles are there in the particle physics. There are so many particles, but I have just mentioned some of them, and their corresponding I3, S, B, Y, Q, and particle content, like what particle has the what quark constitution. So this type of things I have just mentioned here for your convenience, because like when we are going to solve any nuclear and particle physics question, there should be some part of where we have to know that the quark content of K plus. So quark content of K plus will be US bar, and also I3 is half, S is 1, B is 0, Y1, Q1, and all these things. Okay, so this type of things were just prerequisite of our questions and answers. Now I will go for a first question. I think in the last class I was mentioned about that question, and I took that question as a homework for the students, but okay, I think most of the people were not present in the last class, so I am just going to do that question by myself. And if you people have already done that, then it's very great, and otherwise I will do. So the question is basically, it's not exactly core nuclear and particle physics. It has some relativity concept also. So the question is basically, a pi zero meson has the mass m pi, which is 135 MeV by c square, with the momentum 270 GeV by c square, and it is decaying into 2 photons. Okay, now it is saying that if the mean lifetime of pi 0 is 8.5 into 10 to the power minus 17 second, then you have to calculate the how far the energetic pi 0 will travel prior to its decay. So let me write something here. I think most of you have already done that type of questions, but still, like, I thought that it will be a very important question for nuclear and particle physics, so that's why I was just mentioning that type of question. So here basically what they are saying, that pi 0 can go to gamma plus gamma, because it's written the 2 photon. So and what they are mentioning here, m pi is 135 MeV, and you have to just carefully check each and every unit for nuclear and particle physics questions, because you can see that here m pi is in MeV range, but momentum is in GeV range. So we have to convert GeV into MeV or MeV into GeV, whatever you can do, like whatever will be very convenient for you. Okay, so and the momentum, that means m pi is also given, sorry, p pi is also given, like it is something 270. I am taking all the things in MeV range, so that means 10 to the power 3 MeV by c square, something like that. So and after that mean lifetime is also given here. Now we have to calculate how far the energetic pi 0 will travel prior to its decay. So sorry, the question is basically, before decaying pi 0 to gamma, how far it will go without decay. So the main question is basically x is basically the v into t prime. We all know that it is a v into t prime thing, and t prime can be calculated from the relativity equation. So if I just write here t prime, what is basically t prime? T prime can come here, Okay, just a minute. And v, so we have to know the v as well as t prime. So how can I get the t prime value? T prime value can be given by that gamma into t. You can know that gamma is basically 1 by root over 1 minus v square by c square. So gamma is basically 1 by root over 1 minus v square by c square. So if I put these values, like whatever they have given only m pi and p pi value, and we have, and t value is also given. T value, I think it was somewhere 8.5 into 10 to the power minus 17. T is 8.5 into 10 to the power minus 17 second. So this is also given. So now what we have to calculate? We have to calculate at first gamma, and after that we have to put this gamma in t prime equation. Then we can find the t prime value, as well as we have to find the v value also. Okay. So for that we are going to put one simple equation coming from the Einstein, that mass energy conservation, that equals to mc square. I think all of you know this very energetic and very important equation. So equals to mc square. Mc square means it can be written as a gamma m0 c square. Here m0 is the rest mass for that particle. Now coming to the E value. So what is the expression for E? E can be written as p square c square plus m0 square c to the power 4. I think you all know this equation also. So gamma m0 c square. So if P is known to me, m0 is also known to me, this m0 is also known to me, and obviously c square means whenever I will put the m0 or p equation, then c square will cancel out. Then I can find obviously directly the value of gamma, right? So if I just put these values here, like p was something 270, okay. So p was what? 270 into 10 to the power 3, then square, plus m0 was I think 135 MeV it was there, whole square. It will be gamma into 135 whole square. So if I calculate these things in calculator, then it will come as like I totally forgot, but I think 2 into 10 to the power 3, something like that it will come. So this is the value of gamma. Okay. Now gamma is what? Gamma is 1 by root over 1 minus v square by c square. Fine. Then we knew the value of c. So obviously, and also in the left hand side we know the value of gamma, so that from that equation we can have the value of v as well. So from that calculation I can also find the v value. Now you can see here, as I already knew the gamma value, then I can also put this gamma in t prime equation. So t prime will be 2 into 10 to the power 3 into t was 8.5 into 10 to the power minus 17. So that type of equation will be there, something what will be so 17 into 10 to the power minus 15, no 14, something was there. Okay, so you can see that equation of the value of t right now. And if I just t prime, now if I just put t prime as well as v can be found from that equation, as I already told you that gamma is given here and 1 by root over v square minus c square is given. So that means from here I can see the value of v also. So this v will also be given, and after that we can just put here v as well as t prime, then it will come as x value. So this will be the answer for that question. So I don't want to calculate all these things. It's a very simple numerical calculation. So I think you people can already also do that calculation. So the calculation is basically simple. So basically the main thing was that x equal to v into t prime, and we have to calculate v as well as t prime so that we can have the x value. So this was for the first question. So it was not exactly related to nuclear and particle physics. It's totally based on relativity. So this is the first question. Is there any problem on first question? Can you please tell, like if there is any question or if there any problem, you can tell me within my lecture also. I don't have any problem. So is it understandable by all of you? Can you please tell yes, no, yes, or unmute yourself, whatever. I think it will be very, it is already understandable by each and everyone. Yeah, no problem. Thank you. Okay, now coming to the second one. Okay. The second one is basically totally based on nuclear and particle physics. Okay, so as I already told you that most of the question will be on nuclear reaction and all this, so I have mentioned some of the example of this question. Like, okay, let me first read the question. The question is like, determine which decays are allowed. That is the first part. Then for the ones not allowed, you shall tell which conservation laws are broken. Second part. And the third part is, if a decay is allowed under certain circumstances, then this shall be mentioned. Okay, so this type of three part was there in that question, and obviously for this question 5 equation is there. So what the question is basically means, the question like I am taking only the first one. So for that nuclear reaction, you can see that it is a nuclear reaction that P goes to N plus E plus nu E. So this type of like nuclear reaction is there. Now they are just asking that determine which decays are allowed. Like at first we have to check that this nuclear reaction is allowed or not. That is the first one. If it is allowed, then you have to say that okay, this is allowed. And if it is not allowed, then you have to say that why it is not allowed, like which conservation law are broken in this nuclear reaction. And also if a decay is allowed under certain circumstances, then this shall be mentioned. Like if it is allowed, then how it is allowed, something like that. So coming to the first question, I think I will not do all the questions, but as today is the last day, so I will not give you any homework also. But okay, let's see how many time will be there. Okay, so just come to the first one. The first one is that P goes to N plus E plus nu E. These type of questions are very simple. Like if you just understand the trick of that question, then you can easily solve these questions. So I will tell you the simple trick of this question. Okay, I think I have already told you in the previous lectures also, but as today there are so many students, so that's why I thought that it will be useful for each and everyone. So the first thing, what should I do? Like in any question, as I already mentioned in that first slide, I will show you once again. Yes, this one. You can see that here I have mentioned B, L and Q should be conserved in all nuclear reactions. So for any nuclear reactions, we have to check that is it baryon number conserved, is it lepton number conserved, or is it electric charge conserved. If any of the things are violated, then obviously that nuclear reaction will not be possible. Okay, so just before going to all the questions and all the things, we have to first check B, L and Q. If these three are allowed, then we can say that okay, then we can say that the expression, the nuclear reaction is allowed. But for some exception is also there. I will tell you what is the exception for these things. But let me first check that B, L and Q are conserved or not for that reaction number A. Now coming to the B part, B is baryon number. So in that left hand side, okay, I think I will write here so that it will be good. N plus E plus nu E. Okay. Now B is the baryon number. Baryon number, like for proton the baryon number is 1. For neutron the baryon number is also 1. As this electron and positron and electron neutrino are not a baryon, so the baryon number will be 0 for them. So you can see that the delta B, like conservation means like that the delta B should be 0. So here in this case delta B is actually indeed 0, because in the left hand side, right hand side is 1 and left hand side is 1. So that means delta B equals to 0. Now coming to the lepton part. Lepton, like for proton lepton is 0, for neutron lepton is also 0. Positron means it's a minus 1 because electron has a lepton number plus 1 and nu E has a plus 1. So you can see also that delta L is also 0 here. Okay, fine. Now I am coming to the Q value. Q should be, I think, 0. See, Q is 1, Qn for 0, E plus is 1 and nu is 0. So that means delta Q equals to 0. Now you can see that B, L and Q, these three quantum numbers totally conserved by this nuclear reaction. Then I can say that this equation is allowed. But there is a but. So what is the but here? The but is like in that equation, if I just see carefully, you can see that in the left hand side proton is there, in the right hand side neutron is there. As you all know that the mass of proton is less than the mass of neutron. Okay, like if I think that proton is at rest and it will decay as neutron plus E plus nu E, then this type of expression should not be allowed through the energy momentum conservation, like energy conservation. It is obviously allowed by baryon, lepton and charge conservation. That is fine, no problem. But each and every nuclear reaction should be conserved in energy also. So in that sense, if MP is less than ML, so that we can't have that type of expression allowed if proton is only at rest. Okay, now let's say, like someone can ask me, okay, if proton is at rest, at that condition the nuclear reaction will not be possible. That is fine. Now let us consider that, okay, proton is not at rest, or proton is inside some nucleus or something, or it is energetic, something like that. Then is it possible or not? Yes, then only it is possible, because at that time the kinetic energy as well as the potential energy as a whole, the total energy will be like that, the total energy for neutron will be much smaller than total energy of proton, so that type of nuclear reaction will be possible. But if I say that the proton is at rest, then the nuclear reaction cannot be possible. So this is the main thing. Now, so that means the first question, like as it is mentioned that to determine which decays are allowed. So for A, the nuclear reaction should not be allowed in that condition that proton is at rest. If someone told you that, okay, proton is not at rest and it is with some nucleus, then we can say that, okay, if E of P is greater than E of N, only that type of condition can tell you that this type of expression, this type of nuclear reaction is allowed. So this is about the first one. Okay, now coming to the second one. Second one will be very simple. Like I am just telling only in one line it will be solvable. Okay, let me write the second one. Second one is pi plus going to, what was that? E plus gamma. Okay. E plus gamma. So this is the expression. And at first what I told you that B, L and Q should be conserved. So let me check first B. So for B, pi plus is 0, gamma 0, E 0, that is fine. That means delta B equals to 0. Now coming to the L. See here pi plus is not a lepton, so that means 0. E plus is a lepton, that means minus 1 because E plus is there. And gamma is not also a lepton, so that means 0. Now if I calculate delta L here, that means delta L will be minus 1, which is not equals to 0. And obviously in each and every nuclear reaction, B, L and Q should be conserved. In that condition, in that nuclear reaction, as L is not conserved, then we can immediately say that, okay, pi plus goes to E plus gamma is not allowed. So this is the second one case. Okay, we don't need to check all the quantum numbers whatever I have mentioned in the previous, at the I think first or second slide. We don't need to check each and every one. We have to check only three things, B, L and Q. So if B is not conserved, then okay, no need of checking other thing also. But if B is conserved, then just check L. If L is not conserved, no need of checking other things. You can always tell that our nuclear reaction is not allowed. So that type of thing is there. So that means this B is also not allowed. B is also not allowed. Now coming to the C1. I think, okay, I will tell a little bit on that. Okay, mu minus goes to E minus nu E bar nu mu. Okay. Mu minus goes to E minus plus nu E bar plus nu mu. For here also I can tell B, L and Q. So B means here all the things are lepton, so that means delta B equals to 0. Okay, lepton. Now coming to the lepton number. So it is minus 1, no, plus 1. This is plus 1, this is minus 1, this is plus 1. So if I calculate, then obviously delta L equals to 0. Now coming to the Q value is minus 1, 0, 0. So delta Q is 0. Now as B, L and Q all have conjunct, and also you can right now check that M mu minus is obviously greater than M E minus, then we can say that okay, this type of equation is possible, that type of nuclear reaction is allowed. So the answer of this C is, it is allowed. Now coming to the fourth one and fifth one, I think, okay. So for D, I'm just taking here very small thing. So let's check B. For pi 0 is B 0, mu 0, 0, 0. L, pi 0 has 0, mu minus has plus 1, nu is 0, nu 0, 1, sorry, nu is 0, 1. And E minus is also 1. So you can see that here delta L is not equals to 0. That means that D is also not allowed. Okay. Now coming to the fifth one. Fifth one says that N goes to pi plus pi minus. Okay, I think I may have space. Okay, yes. N goes to pi plus pi 0, pi minus. So here just check again B. So B means N is B, and like N is baryon, so that means for N the B value is 1. Pi plus pi minus, these are not baryons, so that means 0, 0. So here you can see that delta B equals to minus 1, which is not equals to 0, so that means N goes to pi plus pi minus, that is not allowed. Okay, I think I have done all the 5 questions. It's a very simple question, and you can also answer all the questions very simply, because we have to just check B, L and Q, and after that if all the things are satisfied, then you just you just check that mass of these things, like mass of the particles and all these things, then it will be very simple for you. So I think this type of question is also done. So can you please tell, is it understandable by you or not? Or otherwise, if there is any question, you have to just tell me the question, that if there any question. Sorry. I think there is no question, like all the things are already very much good. Okay, if there is no question, then I will go for the next one. Okay, now coming to the next one. Now coming to the next one means this type of questions are very simple, and it's only a multiple choice question, because I thought that in the last class we have to just refresh our mind, so that's why I put only some simple MCQ type questions. So okay, the third question is, why do we have decay with alpha emission but not with proton emission? Like, what is basically the meaning of that question? Like, you can see that in alpha decay, that radioactive decay, we can have X goes to Y plus alpha twofold, right? And I think it is ZA, and it is Z minus 2, A minus 4. So this type of expression is there. So they are just asking that why alpha is going as an outgoing particle, not as a proton. Okay, so the option is like the proton is too light, the proton has too small charge, alpha is loosely bound, alpha particle has high binding energy per nucleon. This type of 4 option is there. So what should be the correct one? The correct one will be the fourth one, because the alpha particle has high binding energy. As we already know that its value, I forget its value, that binding energy per nucleon, but it's too high. Okay, so as its binding energy is too high, so that means it can make a particle as alpha particle, and it will throw out from that particle, like from that X, as a whole particle. So if alpha particle has high binding energy per nucleon, then only we can have the alpha emission, but not proton emission. Let's say proton has much binding energy than alpha, then we can have a proton emission instead of alpha emission. So for that question, it's a very simple question, and the correct answer will be D. Okay. Now coming to the fourth one. Fourth one was also a very simple question. Which of the 4 fundamental forces make it possible to accelerate protons? Now there may be there may be some confusion about 2 of the option. Okay, so what does this mean? Which of the 4 fundamental forces? We all know that these 4 are fundamental forces. So which one is possible to accelerate protons? So proton is like P. Okay, so you can see that the proton is like it's within a nucleus, it's present within a nucleus. Okay, now they are asking that which force is possible to accelerate protons, and it should be electromagnetic, not strong. There may be a confusion between strong and electromagnetic, because at the very first you can tell that okay, proton is participating in strong interaction, so that may be possible for accelerating the protons, but it is not that, because the protons the accelerating for the protons is only responsible by electromagnetic force, because electromagnetic force means that as the proton is a charged particle, so that means the electromagnetic force will be applicable for protons. And if I just put a magnet on, like if I put a electric field in between that proton, and it will feel the force, then it will accelerate, and we will give some force of that, then it will accelerate. So basically for accelerating the protons we are only using electromagnetic. There is no connection of strong interaction. So for making it possible to accelerate protons, it is obviously that electromagnetic force will be the main one. And you can say that as an example, like I'm saying that LHC. Okay, so LHC means the Large Hadron Collider. So it's a current experimental setup for nuclear and particle physics. So for that case, what we are doing here, we are just accelerating protons with very high energy. You can say that it's like 70 eV and all these things. So this type of high energy protons are accelerated through only electromagnetic force, not only on strong force. And obviously weak and gravity will not be there, so no need of discussing about these things. So the answer will be electromagnetic. Okay, now coming to the fifth one. Fifth one means the short half-life of a nuclide means. Okay, this type of this question has a little bit discussion, it's needed. So short half-life for a nuclide means. So short half-life means what? I'm just telling at first what is the meaning of short half-life. Let's say one nuclide is there which is X. Now short half-life means half-life is what? Half-life is T half. So T half is short for X. It is showing that short half-life. Okay. Now short half-life for a nuclide means what? Okay. So as we already know one expression, that lambda equals to ln2 by T half. This is a very famous expression for radioactive elements. So basically what it is means that lambda proportional to 1 by T half. So if T half is short, as it is mentioned here, short half-life, then obviously lambda should be much more, right? So lambda is what? Lambda is the decay constant. So the option was it has lower decay constant, but obviously it is not a lower decay constant. As t is lower, then lambda will be greater, then it will not be the possible one. It's a high, it has a higher decay constant, then it's fine. Okay, now coming to these two, in any, you can see that in MSQ type question there is more than one correct answer should be there. So it may be possible that we got one correct answer, that is not the meaning of that we got the total answer. It may be possible that some other answer will be the true one. So let's take B and C also. So B is what? The activity for a given number of atoms is higher, and same thing is lower. So activity is what? Activity has a definition. I have already told, I think first or second lecture, that activity is basically lambda into n, where lambda n0 e to the power minus lambda t, something like that. So here lambda into n. So lambda, like as I already told you, lambda is much larger because t is very small. So if lambda is much larger, then obviously A should be very much. So the activity for a given number of atoms is higher. It will be the correct one, and it will be not the correct one. So the answer of this question will be B and D. I think there should not be any question, or if there is any question you can ask me. Otherwise I will go to the next one.
Hello ma'am, what is the meaning of higher atom?
Higher atom? What?
Yes.
Where? Higher atom?
In the option B.
D.
What actually mean B?
The
Option
activity.
B.
The activity. No.
Yes.
Higher atom. Not higher atom. The activity for
Atom is higher.
yeah, the activity for a given number of atoms is higher. The activity, they are mentioning activity or higher is or lower. So I was talking
What
about.
is it mean?
Yes, activity means basically, see, wait, activity is like A, like this is a term, this is a parameter for defining a nuclear reaction. So activity is like, basically activity is lambda into n. So activity means one nuclear reaction we are talking about, one nuclide radioactivity we are talking. So for that nuclear radioactive, how much decay is going there, so how much active that nuclear reaction is. So that type of thing is basically activity for that nuclide. So here the expression for A is like, A is lambda into n. So A will be much when lambda will be greater, A will be small when lambda will be small.
Okay ma'am, clear.
Okay, so
Now it is
yeah.
yes.
So here T half is small, so that means obviously lambda is greater. So if lambda is greater, that means A should be greater. That's why it is written the activity for a given number of atoms is higher. It is not that higher atom. The activity is higher. Okay?
Yeah. This is my fault.
No problem. Okay.
I was assumed that the atom is very high.
No. The activity will be high. Okay.
Okay.
Okay, now coming to the sixth one. Okay, sixth one is a little bit some theory based question. So what is the purpose with the moderator water in a fission reactor? So I think Sir Paulos has already told you that what is basically fission and fusion reaction and all these things, and also we have to use some moderator water for that fission reaction. And moderator means maybe it will be a very high water, that means D2O, deuteron, or neutron something. D2, no, not neutron, sorry, deuteron will be there, or I think some graphite is also using for moderator and all this. So what is the purpose for this using of moderator water in a fission reactor? So it's a very simple theory question. So it will be the answer will be like, slows down the neutrons to thermal velocities, and also the absorbs the released energy and the transport the released energy out of from the reactor. So I will not exactly explain what these terms means, because if I want to explain the terms what does these terms means, then we have to explain full fission reaction and all these things, but I think you have already read about fission reaction. So in that fission reaction we need a moderator. This moderator should be such that it should be slow down the neutrons to thermal velocities, and it should absorb the released energy, and it should transfer the released energy out from the reactor. And this first option will not be there because there is no connection with the protects the uranium fuel against air. There is no connection between moderator and fuel against air and all this. So the answer of this question will be B, C and D. I will not go to the details of this because it will take so much time, that how it is coming, that moderator, water is fission, doing all the works. But I think you all know these things, so that's why I was just putting as a question here. Okay, now coming to the 7th one. Yeah, that is a very interesting question. The question is, fission fragment are radioactive. Okay, what is the most likely way for them to decay? So at the very first, if you understand that what is fission and what is basically fission fragment, then you all know that fission fragments are like okay, fission is what? Fission is like, let's say, a very high nuclide. It will break into nearly equal or same nuclide particles. So if I am talking about uranium, I think like some Z and A value is there. I think it's 238 or something. So, and it will come as krypton or argon, I forget these things, but maybe something is there so that it will have a very nearly or equal amount of mass number and a proton number and all these things. So this type of thing is fusion reaction. So fission reaction. So the question is, fission fragment or radioactive. So we are not talking about this expression, we are talking about these fission fragments. So fission fragments are basically in that expression krypton and argon, if I correctly know. I totally forget this outgoing particle, but let's say krypton and argon. So they are asking that fission fragment are radioactive, that means krypton and argon are radioactive. So what is the most likely way for them to decay? That means if radioactive particles are there, then how it will decay? And it's very nearly very much possible to decay into B minus, that means beta decay. Because why? Because let's say, like, I forget this Z at A number, but as I already told you, that fission expression means that it should be very nearly equal or maybe equal or something. That means A or Z value will be very similar. So similar means obviously this type of things will be most probably very similar. So if this one is radioactive, then it will obviously wants to go to this one. So it will only possible to go there through beta minus, because in that beta minus only one nuclide is not nuclear, that is Z value, one Z value is changing. So, and also it will come as a stable particle only through the beta minus decay. So that's why we are talking about what is the most likely way. The most likely way is beta minus decay. So this is the answer of D. Now coming to the 8th question. The 8th question is a very simple question. In nuclear reactions, the mass number A must be conserved. This is a special case of a more general conservation rule, which? Okay. Oh, someone is coming. Okay. So the 8th question is, in any nuclear reactions, mass number must be conserved, and yeah, I have told you before that B, L and Q should be conserved, right? So B means baryon number, L is lepton number and Q is charge. So baryon number is basically what? Baryon number means like the baryons whatever present in our nuclide, that should be conserved before and after nuclear reaction. That is the main thing. So if in any nuclear reaction I am talking about A must be conserved, that means obviously baryon number is conserved in this nuclear reaction. How? Because you can see that for A is what? A means the mass number. For any particle, let's say calcium, I am talking about calcium. Calcium has 20, 40. So 40 is the A value, right? A is 40. So 40 is A means it's basically the number of proton and number of neutron. So if A is conserved in any nuclear reaction, that means number of neutron and number of protons are also conserved in that nuclear reaction. And obviously neutron and proton are what? They are the baryons. So if A is conserved in any nuclear reaction, that means baryon number is also conserved in that nuclear reaction. So what the question means? The question means that the mass number A must be conserved. This is a special case of a more general conservation rule. The more general conservation rule will be baryon number. Because if baryon number will be conserved, then only we can have the A conservation rule. As A is basically the sum of two baryons. That is a very special case of more general conservation rule, baryon number. That's why the correct answer will be baryon number. I think it is understandable. Do you got the point? Maybe yes. Okay.
Yes, ma'am.
Okay. So that is the main. So the question is a very interesting question. I thought that the general conservation rule was baryon number, and from that general conservation rule, the special conservation is mass number, because obviously mass number is the sum of the two baryons, proton and neutron. Okay. Now coming to the ninth one. Ninth one is what? Ninth one is a pi plus meson has an average lifetime of 26 nanosecond before decay. What can you conclude about the interaction responsible for the decay? So as I have already mentioned in that previous slides of my today's lecture, there were some tables. Okay, so just similar to this table, I can also make a table for which type of nuclear reaction is possible, for which decay time or whatever. Like I can also make here strong, weak. Coulomb means basically EM. Okay, now okay, just a minute. Let me write here Coulomb and hadronic like that. Strong, weak, or I am also writing like that, gravity. So here the time of decay or average lifetime. Average lifetime is obviously related to time of decay. So strong. Just a minute. I think I should write like that. Okay. So I am writing here average lifetime. Average lifetime. So average lifetime for strong nuclear reaction, average lifetime will be 10 to the power minus 23 second. For weak, it is like 10 to the power minus 13 to 896 second. 896 a typical number for neutron decay, so that's why I am just mentioning that. For EM, it is like 10 to the power minus 21 to 10 to the power minus 16 second. And for gravity, it is infinite. Okay. So these four type of nuclear reaction is there, and if in any nuclear reaction the average lifetime we know, from that average lifetime we can also know that what type of nuclear reaction it is. Is it strong, weak, EM or gravity? So here for pi plus meson, what is given here? Pi plus meson has an average lifetime 26 nanosecond. That means 26 into 10 to the power minus 9 second. Then can you please tell me which type of range it is? Like, it's given that 10 to the minus 23 means strong, 10 to the minus 13 to 896 means weak, 10 to the minus 21 to 10 to the minus 16 second means EM, infinity is gravity. So this type of average lifetime is responsible for which nuclear reaction? Can you please tell anyone? Is it strong, weak, EM or gravity? I have already given the range here.
Weak.
Weak, yeah, great. Because it's 10 to the power minus 9. So 10 to the power minus 9 means it lies in that range of 10 to the power minus 13 to 896 second. You can also see here one difference in that average lifetime, that for strong nuclear reaction the average lifetime is very short, only 10 to the power minus 23 second. For EM it's still long, 10 to the minus 21 to 10 to the minus 16. But for weak it's a very long, like 10 to the minus 13 to 896 second. Like for some particles the average lifetime is also 896 second. So it's a very huge time, obviously with respect to 10 to the minus 23, 21 and all these things. Okay, so just it is also a very important table, I can say. So if I just mention here as a table form, then it will come like that. I did not mention as a table form, but I was just writing here. Okay, now coming to the 10th one. 10th one is a little bit elaborative. Okay, so the 10th one is the long lifetime of the pi plus meson makes it fly rather long distance before decay. It often travels with a velocity close to c. Actually, there is a well-known, at least to some, relativistic effect which changes the average flight length before decay as observed in the laboratory. What is the result of this effect? Okay, now what does this mean basically? It says that it is basically very similar to the first question, but okay, let me tell again. The question shows that the pi plus meson, this pi plus meson is going to fly before decay. So it is going to fly, and pi plus is going to fly with the velocity of very near to c. That means this type of condition is for what? This type of condition is for relativistic particle. Like if you have that type of condition that velocity is very near to c, then you have to consider the relativity in that particle. Okay, now pi plus will fly with the velocity very near to c, and they said that there will be a relativistic effect which changes the average flight length before decay as observed in the laboratory. Now in the very first question I have mentioned one expression, that x equal to v into t prime. So as you already know that the time dilation, okay, for relativity, so for any relativistic particle, if it is flying with very large velocity very near to the speed of light, then its time diluted. Okay, so in that frame of reference the time is diluted. So if I am taking that type of concept in our mind, then t prime is diluted. That means t prime is longer. Now as x equal to v into t prime, that means x will be more longer. That means the result will be longer flight length. Longer flight length will be the result of this effect. So that the expression will be the A1. Okay. Okay. Now coming to the 11. Yeah, 11 is very simple question. 11 says that the area of a nucleus is proportional to some power of the mass number. So we all know that R equals to R0 a to the power what? Can you please tell? A to the power something what?
1 by 3.
Yes, 1 by 3. So R is what? R is the radius. Now they are talking about area. So area is what? Area is basically pi r square or any r square. But basically I am talking about r square. So the r square means r0 square a to the power 2 by 3 because it is 1 by 3. So r0 is a constant, r0 square is also a constant. So that means it will be a by 2, a to the power 2 by 3. That means a will be 2 by 3. It's a D option. It's fine? I think it's fine. Okay, now coming to the 12th one. For 12th one, I will tell you some theory. I think 5 minutes is left. Okay, it will be okay. So the 12th number question is the phenomena in which proton flips is what? The phenomena in which the proton flips. Proton flips means basically the spin of proton will flips. Like if the spin of proton is plus half in any nuclear reaction before, and after that its spin changes to minus half. That type of things is known as proton flips. So the phenomena in which
Option D.
hello.
So I was saying that the option D is right, ma'am.
D na B.
Yes.
Which
D.
nuclear magnetic resonance?
Yes.
Yes, that's correct. Right. I think that you people not that much familiar with NMR, so that's why I was talking about NMR. Just a minute, someone is coming. Okay, so I thought that NMR should not be known to each and everyone. So I was just talking about some more on NMR. So NMR is basically nuclear magnetic moment, as you already told correctly. So it's one experiment. Which experiment it is? The experiment works when a spin flip between the energy levels occurs. The energy difference between the two levels corresponds to the energy of the electromagnetic radiation of a different wavelength that causes the nuclei to change their energy levels. So the phenomena of proton flips occur in one and only in NMR, the nuclear magnetic resonance. So this type of thing is there. Now I will now my question and answer session is over, and I think 3 more time is there, 3 minutes. So in that 3 minutes I will tell you something very interesting, which yeah, someone is saying something. Okay. So now coming to the last portion of my talk. The last portion will be very interesting for all of you. Okay. So what is the last portion? I will not show you right now. I will show you after some time. Can you please mute yourself? I don't know who is gravity physics.
Gravity. The name is Gravity, is saying someone.
Okay. Thank you so much, gravity. You muted yourself. Okay. Uh, yes. Now, in that whole nuclear and particle physics course, what you have learned that our fundamental particle is like lepton and quark, because as you all know that quark and like all the particles will made of quark and lepton. The all the baryons and mesons will made of quark, and all the leptons will be made of as a lepton only, because lepton is a fundamental particle. This type of things we already knew, right? Now I will tell you something more interesting. The interesting thing is there some recent research, like it is not exactly verified till now, and obviously you can also think that quark as a fundamental particle, it is also not experimentally verified till now. So recent experiment shows that there may be some more fundamental particle within that quark. Like we don't know much about quark, we don't know much about lepton, we don't know anything about the very fundamental particle of our nuclear and particle physics. So it may be possible that there is some theory, it is not experimentally verified till now what I am going to say. Some interesting research experiment told that it is not that quark is the most fundamental particle, lepton is the most fundamental particle. The most fundamental particle but by which quarks has formed, it may be a preons, P-R-E-O-N s. I am not telling you the prions is the most fundamental particle and it is already experimentally verified. I have already written here, but not experimentally verified. Okay, so you cannot see this type of name in any textbook, nuclear and particle physics textbook, but it is totally very recent experiment, very recent research, which told me that the quark may not be the most fundamental particle. The most fundamental particle will maybe something else, which we can named as prions. And also lepton can also be a composite particle with prions. Here see, prions means that pre-quarks. Prions are in four varieties: plus, antiplus, zero, anti-zero. Quarks are made of three prions. I am not telling you all the details of prion theory, but I am just telling you something interesting, that whatever you have known right now, that quarks and leptons are the most fundamental particle, it may be possible that after some crucial experiment we can found that no, quark or lepton are not the fundamental particle. It may be possible that something else is the most fundamental particle, and this type of theory is also there in our research work, and this type of particle is known as prions. And we did not heard about these things before, so that's why I thought that it may be something interesting, and that's why I told you. So prions is basically a four types variety: plus, anti-plus, zero, anti-zero, and obviously just like that quark model, prion model is also there, and for that prion how quarks and leptons are coming from that prion, that type of theory is also there, but it is not experimentally verified, so that's why we are not taking as a very crucial one. Okay, so I thought that it will be very interesting, that prion thing. And yeah, is there any question about prion? I personally don't know much about prion, but still if you ask something on prion, then you can ask me. But it's little bit interesting for me also.
Actually, I have lots of question about prions, but I stop myself to ask because uh,
See,
it is new.
yeah, it's really new, and obviously like there is one model also, just like the quark model. There is one model about prion, and how these quarks and leptons are coming from that prions also, this is also given in that model, so you can read these things also. But I always tell, I like again and again I am telling that it is not experimentally verified, so don't take it as a fundamental one. I'm just taking as a very side one. So if it will be verified, then it will be a very breakthrough of nuclear and particle physics. But okay, till now it is not verified, so we are not,
Yes.
yeah, we are not that much focusing on that. We will focus on quark model till now, but I'm just taking as a additional information and all this. Okay.
Yes, yes. I am thinking that about anti-zero. We know anti-plus, but what is anti-zero actually?
Yeah.
Zero and anti-zero are
Yes.
uh,
See,
this is
just
totally unacceptable. I mean,
yes,
uh,
just similar like
impossible
that.
to think it.
Yes, just similar to the color charge. We were not thinking about color charge. What is basically color? Color means red, green, blue. Is it really red, green, blue, and all these things? But it was verified that
Yes.
no, it is not basically colored. But we have just assuming a quantum number, quantum charge, assigned a quantum charge to that particles. So just similar to that, we are taking as plus, anti-plus, zero, anti-zero. It is not like that plus, anti-plus. Anti-plus means minus, you can tell, but why it is written that anti-plus? And for also zero, zero is fine, but what is anti-zero? And also for anti-plus, obviously anti-plus should be minus, but why they are not taking as minus here? So this type of question should be there, but right now I'm just telling that quarks are made of three prions and all these things, and if you are interested, then you can read about prion model and all this. So but this is interesting. for me at least. So that's why I was just
Yes, yes, yes. Also for me, ma'am.
yeah.
Is any research paper recently research paper published on this?
Yeah, there are some research papers. I will send you through mail so that you can just read this.
Okay.
Yeah, like
Yes, ma'am.
I don't have that much time to read all these things. So, but yeah, if anyone can interested, then obviously he or she can read this. So, and
Yes,
obviously
yes.
again and again, I am telling it is not experimentally verified. So don't take it seriously that much. But obviously you have to read that because it's a most interesting and most new things. So yeah.
Yes, ma'am. Oh,
Nani,
Yes.
and this prion is somehow connected to the string theory.
No. Basically, sorry. Here, prions are totally different to string theory. Prion is it's a very new theory, I can tell you, and there is no connection between string theory because string theory was considered very before. But it's literally something new, and it's totally based on quark and lepton, and they are just focusing on one thing that no, quark and lepton are not as a composite particle. They are sorry, they are not as a fundamental particle. They are basically the composite of prions. So I think it's not related to string. I'm not sure that it is related to string or not. I can't say that it's not related to, but I don't know exactly what is basically prion. I don't know much about of these things. So maybe it is string, but I think it should not be related to string. I don't know. Like it is not that I know all the things, but
Yes, ma'am. Because of string theory, we assume the smallest thing is a string,
string, yes, string.
but in here we assume is a particle prions. Am I
Yeah,
right?
yeah, like don't ask me any more questions about this because I am also not that much good in prion, but I was just read somewhere that prion may be the most fundamental, and you can also read the recent research work on that, but I don't think that prion is related to string somewhere because as you already told that string is like in string theory they are taking string as a most fundamental one. So, but here they are taking prion as a particle as most fundamental. So maybe it is totally different to string theory. I don't know. Sorry. So, yeah. Is there any other question?
And
Yes.
can you give us any idea how to write exam or
How to write?
exam patterns?
Exam pattern means you are talking about NET gate or NPTEL exam. What?
MPTL exams.
Oh, NPTEL exam. Okay. NPTEL exam. Okay.
It is some
Just
subjective or objective?
yeah, I'm telling. Okay, so just focus on whatever given in the assignment. First of all, just focus on these, then focus on like it is not possible to go through all the lectures whatever given by Paulo sir. It is not possible, that I understand also, but just try to focus on the assignments they are giving in your throughout all the lectures, and focus on whatever I and Archana is teaching you. Like I think Archana was already told you something about the previous year questions. So just try to focus on that. And obviously there will be subjective as well as objective questions. So it is not that only subjective or only objective questions. Okay, so I will suggest
Okay.
you just focus on the assignments very carefully, like this year questions as well as that previous year question whatever Archana is given to you. Like I was taught you, I think within for first 3 or 4 classes I was talking about previous year questions, but right now I am not doing these things. I have just totally gone through differently. So I think whatever she has taught to you people, that will be very important for you, and focus on the recent year assignments, and obviously if time will permit that focus on that lectures also, that will be obviously very good. So like that I can't say exactly what will be the questions and all this. So this.
Ma'am, to be honest, the lecture is not enough.
Yeah, sorry.
Lecture for
Lectures.
lectures. Yes, ma'am. Not enough for the and don't fully understand the subject. Because I'm undergraduate student and the nuclear and particle physics, the basic knowledge of nuclear and particle physics are not in there in the video lectures.
So you told that it is not enough for you to understand all the things in nuclear and particle physics. Uh,
Yes, ma'am.
the lectures by Paulo sir.
Matlab, yes, ma'am.
Uh, yeah. See, actually.
Actually, you should read the specific book, reference book of this course to understand the whole lecture.
Yes, yes,
I
yes.
personally suggest you, Mr. MD.
Which one?
Mm, this is Hari Ram.
No, book. Which one book are you saying?
Oh, this is a special book someone
Green.
for quark model is. Hello. Yes, Kenneth Karne. Uh, Actually, it is on the course page. Some book is some this
Give
full
me
list is there on the
give
course
me.
book.
Uh, I read it.
There is some special book on particle physics, special book on uh, nuclear physics, special book on especially for quark model.
If you will
Okay.
tell me, then I was very much influenced by one book, which is basically nuclear. It's totally on particle physics. I will tell you. That book was Perkins book. So it was really very nice. For me, it was very nice. So you people can also try with that Perkins book. For only elementary particle physics, there is no nuclear physics. Only elementary particle physics, but it will be very difficult for BSc student. Like BSc student means like there will be so many subjects and all these things. mm, but I will prefer that Perkins book. But obviously whatever Aviram and MD told you, that you can also follow. That is very simple books. uh,
Yes, one special book is quark and leptons, an introductory course in modern physics.
yes, yes,
This is
Perkins book,
very
yes.
beautiful.
Yeah. Okay. Is there any other questions, discussions, comments? So when is your exam?
30th October.
Sorry.
Hello.
Huh?
At the hello.
Yes, yes. When is your exam?
Um,
NPTL?
30th October.
30th October. Okay. 30th October means today is 21st. Oh, only 9 days of.
Very,
Night.
yes.
Okay, have you prepared?
हाँ but revision मतलब बाकी है.
Okay, fine. So all the best for your exam to all of you, and I hope it will be very good exam. And just try to feel nuclear and particle physics as not a very serious thing, as a very simple thing. Then it will be very good. And just try to understand each and every line in your book or in your slides, whatever it is given to you. Just try to understand each and every line, so that it will be very helpful for you, as well as for understanding at least. And after that, if you understand very clearly, then obviously the answer and whatever they will give you as a question, it will be very easy to solve. So yeah, I think today is the last day, so I thought that I will tell you something very interesting and very simple things. So that's why I have taken that type of simple questions, as well as at the very last I have mentioned about prion and all this. So yeah, all the best for your exam. Bye bye. It's 7:14. Bye bye. All the best.
Thank you, ma'am. Bye.